Let's recap you 12s. Let's begin. Continuous random distribution. What have you learnt so far? Can I please have Jack tell me what you know about continuous random distribution? Can't remember. Just tell me what is continuous? What's continuous?
It's non-calculated.
Yeah, excuse me guys. Thank you. Sorry, Jack, say it again. A variable that is continuous is a variable such that you can't count the data. Okay, unlike flipping a coin, you can count the outcomes. You got heads, tails, counting colors, black, blue, green, yellow. Number of males in this classroom. Number of cars that drive into the car park. Rolling a dice. Lottery ticket. Yeah, you can count all that. Whereas continuous, it's a variable where you can't. Okay, you can't count it. And therefore making it harder to find the probability. Because probability, if you can count them, you can say there's a total number of outcomes, and find what you want out of the total. That's how you find the probability. So the problem with continuous is when you have data where you can't count it. Therefore finding probability is hard. Okay? Give me some examples of what a continuous variable would be. Can I please have Amir? Give me one. What's continuous? A variable, something that you can measure. Time. See, time, it means like, let's say, the probability of, Mr. Tran running a 100-meter sprint to get exactly 11 seconds and 12 milliseconds. Okay? The chances of that occurring, like, how do you calculate that? We don't know what the time is. What's the total outcome? What's the total number of times that you can have? There's infinite. That's why you can't just choose one instance out of infinity. It's too hard to calculate. If for some reason you can count time as you either run 1 second, 2, 3, 4, or 5, then that was easy to count. Then you can say, oh yeah, Mr. Tran can run 11 out of 5 or 11 out of 10, but you can't count time. Time's infinite. Yeah? So time's an example. Give me another one. Rex, give me one. Your height. See, your height in this classroom, everyone, you could have a few that's 170, but some of us are slightly different. It could be 170.1. One of you could be 170.2. Some of you could be 171. So the measure is harder to count. You can't tell what is the total. You can't say it's 1 out of 10, 1 out of 20. You can't count that. Okay, but you can talk about regions though. You see, the difference between height, if you want to be able to count them, I can do something like this. I can say in this classroom, if I put a category, if I said, how many of you are from 150 centimeters to 160? I count a number of you. So I could say there's 1, 2, 3. Then I could say, what about between 160 to 170? I could say there's 1, 2. And then out of 170 to 180, you see, this is possible to do. When you're talking about a region, so it's every 10, that's my interval, it's possible to calculate now. You can actually work out the region from that, the chances of that occurring. So if I said from 150 to 180, that's a distance of 30. 60 to 170 is a region of 10. So it's like 1/3 of it, I fit in that category. See, that's possible to work out now. I can say 1/3, there's a 30%, 33% chance of choosing someone between 160 to 170. So that's possible. But I couldn't have asked you to say, find the probability of choosing someone randomly here to be exactly 160 centimeters. Because I don't know. What's the total? It's 1 out of 1. So that's a problem. Does that make sense? Yeah? And that's the theory for continuous. If it has to be regions, then now we can lead into the next step. So we now understand that's a continuous. We've got height, weight, time, temperature. All these cannot be measured by counting 1. They're all infinite. So now how do we calculate probability? You need it to be a specific condition. So, what were those conditions? What is this called? What was this called, David? You need some sort of condition. What is it called? There are 2 conditions for this. You don't know, Layla? Yes. What is that called? Good. Something density something. Someone help me, Murray?
Probability density.
Good. Probability density function. So PDF. Yeah. Probability density function, which basically just means what I just told you. I just said the probability. We want to model this. We talked about regions. But what if we can model it with a curve, which is a function? Yeah. So I'm going to call it. This is a curve. Let's call that f of x. Region talks about the area under the curve. Now, if this region is the probability, because that's what I want to use. I want to use this region. I want to say half of this region from here to here, if that was 100%, then half of it would have to be 50%. See, if I want to model it as a probability, the region, I can work it out as the area under the curve. Then if the region is probability, we know two things about probabilities. One, you can't have negative probability, hence you can't have negative area. If you can't have negative area, it means f of x cannot be below the x-axis. So the first condition was f of x needs to be bigger than 0. Makes sense, because you can't have less than 0, sorry, greater than or equal to. You can't have the function or the probability, the area or the region under the curve, it can't be a negative. You can't have negative probability. That's why that's the first condition. What's the second condition? Well, I just gave you the first one. What's the next one? Josh, can you in? Yeah, because if the region represents probability, we've got to remember that. It's the idea that this region represents probability. It can't represent probability unless it fits in the conditions of what probability is. And we knew from the beginning probability ranges from 0 to 1, meaning 0% to 100%. If it's more than 100%, you can't use it to model. You can't use it to predict, the chances of something occurring. That's what we're trying to do. We're trying to say the region is probability. But if it is, what are the things that it can't be? It can't be more than 1, and neither can it be negative. That's what probability density function means. Okay, so they're just saying the area under the curve, when they do this, area under the curve means region. So the region area under the curve, it just needs to equal to 1. We can't have it less than 1, doesn't make sense. All probability should add up to 1. We know that's the chances. That's what PDF or probability density function means. And that's the first step in order to then do continuous random distribution. You can't do this until you have this. It's like a Bernoulli sequence. You can't, if you don't have two outcomes, you can't use binomial. Yeah? It's the same thing here. You can't use continuous unless you know these two conditions are met. That's the logic. Yeah? Then I taught you in, I revised with chapter 14 and chapter 13, and I talked about expected value, the theory, variance, and standard deviation. Yeah? Let's recap, because we're going to use exactly the same things that you're doing here in terms of theory, and we're going to apply it into chapter 15 or exercise 15B. Yeah? What's the expected value again? What's the theory? What's the formula again? What do we know? What is this, Percy? Chapter 13.
It's, I think it's binomial one or...
No, I just want to know the chapter 13. Binomial comes from this theory.
Sum of variables times validity.
Fantastic. Okay, the sum of the variable, remember the distribution I showed you, there's like 1, 2, 3, 4, 5, 6. It makes sense if you want to find the mean, it's 1, and I showed you the proof, times the probability of x equals 1, and sum it with 2 times the probability of x equals 2, and it carries on. All the probability should add up to 1. This is distribution. This is how you find the mean. That was the shortcut to find the mean. Otherwise, normally how you find the mean is you do sum of all numbers divided by number of numbers. But if you follow that method, what you realize is, technically, it's actually faster if you just did 1 times the probability plus 2 times the probability. And that's what that's saying there. Okay, so that was part of chapter 13 to find your expected value, which is your mean. Yeah, mean is the average. Then you had your variance. And I spent a bit of time trying to describe what a variance was. Hopefully we now have an idea. It is the average error. What is my error? Error in prediction. So I have a prediction, I have a mean, I have an average. I'm like, you guys should get an average of 80% in this classroom at the end of year. And then the variance will tell me, well, how off am I? What's my error? The larger my error, the worse. The smaller my error, the better. The smaller my error means less problems, or it's more predictable. Yeah? What's the theory again? What's the formula? Because we're going to use exactly the same one for today's session, that's right. So what's the formula again? Variance is equal to what? What is it equal to? I'm going to choose someone random right now. Who am I looked at? Frankie. How do you find the variance? What's the theory again? Good. It is the square of your x data subtract from your mean. Yes? I see what you're doing. Yep. This is true. This is the computational formula. Okay, to do on your calculator, that's quicker to do. The mean of x squared, so your data, square it minus whatever your mean is squared. But I'm asking for the actual theory. I wrote it, part of it already. So you've got x, remember your data, minus what I predict you, square it so you remove all the negatives, and what else? What am I missing? What am I missing from this formula? I'm missing one thing to make it make sense. So I squared every data. What am I missing? Yes, David. Sorry, I couldn't hear you. No, not subtracted from 1. Think about it. What are you doing just now? You took your data, so you got, let's say 90%. I predicted you get 80. You subtracted it, there was 10 left. So I was 10% off, and you squared it, makes 100%. But for every one of you, I made a prediction. So let's say there's 25 dots right now, 25 errors. What do you do with that afterwards? Logically. What do I do with those errors? Every one of you, I'm like 10 off here, 1 off there, minus 2 off there. What do? Fine? You divide, well, along that idea, you are finding the average of my errors. Because if you think about it logically, if I have 25 predictions, then each one of them has how bad I am at it. I could be -1, I could be +1, I could be 2 off, I could be 10 off, I could be -7 off. What you want to know is overall, see the average. In the long run, overall, what's my prediction? So what you really need to do is find the average of that. So you do -1, +1, +2, +10, -7, and you find the average divided by number of numbers. Sum of them all divided by number of numbers is what you're missing here. So the E just means find the average of that. So here you said find the average of X. Now I'm saying find the average of your error. See, the error is your variance. If you find the average, on average, what's my error prediction? On average, did I make a good prediction? That's what it is. Average means in the long term, did I make a good prediction? Not just for one instance, not for one student, because for one student I could be really off. What about every other student? Maybe I was very close. It was just the one outlier. Yeah, but overall I'm doing pretty good. All right? So that's what variance is, and this is the theory right here, which I'm going to rub this off so you can see. That just means find the average of my error prediction. See, this is your data minus mu, which is what I expect you to get. Your data minus what I expect you to get. Square it so I remove those negative problems. Then I find the average of that. See, finding the average of that tells me overall what's my average prediction. How bad is my error? See, that makes sense. That describes what I'm actually trying to figure out. I want to see, is my prediction good or not? If this was 0, if my average was 0, that's great. That means my error is 0. That means I'm 100% accurate. It means that anything I predict is absolutely correct. Does that make sense? Yeah? So that's variance. Well, the reason why I'm emphasizing on it is just so that you remember the link to chapter 15, chapter 16, chapter 17. They all do the same thing. Okay? Now, let's move on to today's exercise, and I'll come back to these exercises so you can work on it. Expected value and variance. Let's compare. This is what I taught you. I said the expected value in chapter 13 is the sum of your x data, your variable, whatever your data is, times the probability. Then in continuous, it's exactly the same thing. You see, if probability was the region, was the error region, then it was find the area or the region of f of x dx. That is equal to my probability. That's what I'm saying. This is this. So this is summing all the regions. Think about it. Whatever your curve is, if that's my curve, I'm summing them. I'm summing all my probabilities. So that already means sum. F of x to find the region, that's P of x already. What am I missing? See, from the theory, you're saying take your x data. Well, if this is my probability, then multiplying that probability by my x data should give me my expected value. Logically, because this curve, this area is the sum of every probability times x. See, this right here is exactly what that is. It's just that you're applying it to continuous. It's exactly the same thing. So this formula here, you don't have to memorize it. It makes sense. See, it makes sense. You're just saying x times f of x, which is the probability of the curve when you're finding the area. X times this gives you the area. Sum from negative infinity to infinity just means find the error region. The error region should add up to 1. And if I add all the probabilities times x variable, that's exactly the same as what you're doing here. Probability times x variable. It's exactly the same thing. It just looks different. Yeah? But it's only different because this is continuous. But the theory is the same. That means you can also do the same for variance. Variance is exactly the same thing too. See, variance, we said before, the theory was variance of x is equal to e of x minus your data, all squared. All squared. Sorry, all squared. Then it's exactly the same thing when you find the variance. If this is e of this, and this is e of x was equal to this, then the only difference is then e of this, the only thing you're changing is the x. So instead of x times probability, because this is x, that's x, that's x. Then if this is bracket x minus mu squared, that there would be bracket x minus mu squared times function of x. And suddenly, you got your formula for variance. It's the same thing. See what I mean? So that's what I'm saying. The theory applies to all. It's all the same. Yeah? I'm going to show you how we're going to work through it too. I'm going to use the calculator and find the integration. That's all we're doing. All right? Now, let's jump to median. If we understand, well, the first thing to understand this whole chapter is you need to understand the area under the curve is the probability. If it is the probability, we know it has to range from 0 to 1. So that means this whole area has to be 1. Hence PDF function. Yeah? Probability density function. Then the median, if you remember back in year 7, median is the middle number. Middle means 50th item. 50th item means 50%. 50%, 0.5. If 0.5 is your chances of occurring, like your 50% of your data, then that makes sense that probability-wise, this region, this m value, to give you an area of 50%, is called your median. Because it's your 50th percentile. So if you remember back in box plots, you had your quartile 1, quartile 2, and then you got your Q3, which is your median. Yeah, and you got your lowest value to your highest value. Yeah, this is the same concept. Lowest value is from 0 all the way to the top value has to be 1, 100%. This is your 25% point, that's your 50% point, that's your 75% point. So we're just talking about the area, median being the 50th percent. That's why we know the area has to be 50% or 0.5. Okay? If all this doesn't make sense, I'm trying to gel it all in so you can see statistics being 0 to 100%. And the only theory that we've made so far is just saying, what if we can create a curve where the area fits what a probability is? If it fits it, we call it probability density function. That's as simple as it is for chapter 15. Yeah? Every other thing, find the expected value, find the mean, find the median, find the variance, is all exactly the same thing. Everything you've done in chapter 13 is exactly the same. Yeah? So the only new thing I've taught is what a probability density function is. Okay? Now, this is what exercise 15B is. They tell you this is a formula. I'm not interested in you memorizing them. I just wanted you to understand whatever you did chapter 13 is exactly the same. If you had e of g of x, so if x was a variable, a function rather than a variable, then it was g of x multiplied to the probability of x and sum that. Then it's exactly the same when it comes to conditional. So it's still your variable, which is your function, times the probability. Sum them together. It's the same thing. Chapter 13, chapter 15. Yeah? Same thing that one. That one was e of x, x, or e of x is equal to sum of x times probability of x. Well, it's the same thing. X times the probability is the area under the curve. How do you find the area under the curve? Integration of the curve between A and B. Just times by x. That's exactly the same thing. Chapter 13, chapter 15. Yeah? Logically, we know the median is the 50th percentile. So if it's the 50th percent, probability has to be 0.5. That's 50%. So find the area from A to negative infinity to up until a certain value where you have 50%. That m value is called your median. Yeah, just like when you did back in year 7, you had like 1, 2, 3, actually I'll do 8, 10, and 15. I say, what's the median? So what you did was you ordered it from smallest to largest, and you looked and you counted, you're like 1, 2, 3, 4, 5, middle. And you're like, you find your middle and you're like, there's 2 here, there's 2 there, so your middle is 8. But all you're really doing is you're just saying that's your 0, that's your 100, that's the 50th percent, that's your 25%, and that's your 75%. That's what you're doing then. And then we called that minimum, maximum, median, quartile 1, quartile 2. Then you learned range and interquartile range. All of that was just leading back to this idea. Okay? So it's called statistics. But anyways, rub that off in case you're all confused by adding on extra information there. All right, now, let's do this question. Let's do this question together just to consolidate a bit of understanding, and I'll use a calculator to show you too. Find the expected value of the random variable x, okay, which has probability density function. See, if you see this in the exam, you should be thinking of probability density function only means continuous variable. If you don't see that, then it's probably a discrete problem. If it's discrete, you've got chapter 13, 14. If it's probability density function, you already know there's 2 conditions. That f of x has to be above the x-axis, and the probability has to add up to 1. That's the first thing you need to know. There's 2 conditions to it. So all the questions that are the application or the harder questions of exam 1 to do with conditional, they're going to make sure that you're testing these 2 points. Is the curve above the x-axis, and is the area under the curve equal to 1? That's all they're asking. Okay, so let's roughly sketch this. F of x is a hybrid function. So I'm going to do this. It's got 0 to 2, so 0 to 2. And anything less than 0, it is 0. So when x is less than 0, I have a curve, which I'll color in blue, 0. This is my 0 line. Anything greater than 2, it's also 0. There you go. Now I just need a sketch between 0 and 2. Between 0 and 2, I've got 0.5x, which really means the same thing as saying y equals half x. That's a linear equation. Half x, if I look at it, it's a gradient of 1 over 2, which just means every 2 across, you move up 1. So that just tells me every 2 across, 1, 2, and move up 1. There we go, that's my next coordinate. There we go, that's my line. That's my straight line. So now, apparently, according to probability density function, I should know one thing. The area under that curve has to be 1. Well, let's test it. That's technically a triangle. See right there, if I found the area of this, let's see if that's true. Area of a triangle, half base times height. Height is 1, base is 2, so half times my base, which is 2, times 1, and voila. Area does equal to 1. Great. So that just means this can model a probability density function. Yeah? But the question wasn't asking that, I was just trying to show you that when they say probability density function, those are the 2 things you should know. The graph is obviously above the x-axis, and the area does sum up to 1. If it does, it's a PDF function. Okay? If it's a PDF function, means you can find the probability. That's it. Okay? Now, what's the question? They say find the expected value. So E of x. Now we know the theory. E of x was the sum of x times the probability of x. But because we're doing continuous, and we know because it says PDF, then this is the integration from negative infinity to infinity, meaning the area under the curve x times the probability. Now probability is f of x, area under the curve, dx. That's what we're trying to find. We're trying to find e of x, which is that definition there. So if that's my definition, well, let's have a look. It's not negative infinity to infinity, because negative infinity, I know that's 0. So where's my endpoint? My endpoint's right at 0. So instead of negative infinity, it should be 0 to 2. So that's the area I'm looking for. Yeah, everything else is 0, so I might as well just find out the area here. 0 to 2. My f of x curve, well, it tells me it's 0.5x. So I'm like, all right, well, f of x is 0.5 times x. That's my, if I found this, just that, without the x in front of it, and I did the x, that's technically just says find the area under the curve, which is probability. If this is probability, we said take the probability times x. So that's what I'm going to do. I'm going to write, all right, times by x. If you have this in your exam, just type it in your calculator. Solve for that. Because whatever that value is, that is your mean. That's your mean. So from 0 to 2, find your mean. Yeah? So here we go. We do it by hand. Integration of 0 to 2. Expand the brackets. That becomes half x squared dx. And you're back to chapter 11. See, chapter 11, I can take out half as my constant. Half 0 to 2 of x squared dx. Now let's work this out. What is the integration of x squared? What's that equal to? Just did your sack, so you should be able to do this. Good, x cubed on 3. So it's x cubed on 3 between 0 to 2. Remember, I took out the constant half. Using fundamental theorem of calculus, sub 2 in, sub 0 in. So you work that out, that's half. Multiplied 2, sub 2 in, that's 8 on 3. Subtract sub 0 in, that's 0. So that works out to be 8 on 6, which is, what's that? 4/3, is that right? 4/3? Which is about 1 1/3. So 1 1/3, that's my average, 1 1/3. Voila, that value there is my average. That's my mean. Is that easy? Yeah? See what I'm saying? I'm just trying to say, whatever you learned in chapter 13, you're doing exactly the same. You're just applying chapter 11 skill here. Okay, so whatever you know how to use a calculator for integration, that's what you can do here. Okay, now, let's try this on a calculator so that we get familiar with how to use a calculator. Now, if you have a CAS, bring it up. Let's do this. TI. Just making sure that you can use your CAS and some shortcuts that you might know. Not to a USB. I got a connector to. I don't know if that helps.
Transfer operating systems.
Yes, with this one. Alright, here we go. If you were starting this problem and you didn't know how to do this, control doc, add a graph, so number 2. Your first job, if you couldn't draw it by hand, you can draw it on a calculator. Yeah, you can draw it on a calculator. If you couldn't figure it out, draw it on a calculator. So in your catalogs, right next to the book, so right next to the book, or next to the 9, that's your common function. So if I go to that, there's a 100 function here. You can use that and type it in. And in our case, we had three of those functions. Was it 3 or 2? I think it was 2, yeah? So it was only 2. You either had that, and I said it was 0.5 times. Don't forget the times. That normally happens in your SAC. Some of your students were asking me when I was walking around. 0.5, if you just put 0.5x, sometimes in an equation, a large one, they can't tell the difference between times x and not times x. Okay, and that's why they can't solve. So make sure to put the times. So 0.5x, and that was between x is greater than or equal to 0. So greater than or equal to 0 and less than or equal to 2. Yeah? And the other one was it will be 0 if x was greater than 0 and x is, greater than 2 and less than 0. Okay? So I've just put in my conditions there and we type and there we go, we've got our graph. See, if I just zoom it in, you can see that's my graph. So if you didn't know it, you can still draw it. That's my graph there, 0 to 2. The other thing that I noticed from your Sachs, if you didn't know how to zoom, you could do a couple things. Menu, 4, which is your window and zoom. There are 2 ways here. I like to use the 1 because I can adjust it myself, okay? But if you find that you can't adjust it yourself and you don't know how to close in the domain and the range, you can use, I like the other one, which is a box, zoom box. Zoom box is nice because you can select where you want it to be. So let's say I select one corner, so I'd say this corner, I select here, and I select the second corner.
What if it's too big?
If it's too big, yeah, then
Zoom out.
zoom out, but I like this particular zoom. If it was too big, I normally go Windows, 4, and I go zoom fit. But the only thing with zoom fit is it works best if you have the domain right. If you got
Circular function.
yes, then this becomes a problem. So if you have the domain right, if you've got the width correct, this will adjust the column, so how high it is. So that's nice when it's really big. Otherwise, I always go back to Windows settings. Okay? Anyways, here we are. We got that, and you want to find the area. You can do it in your analyze as well. You can go analyze, and you can do integral. Integral means find the area under that curve, so you can do integral, and you can all the way to the end point. Ah, there we go. And it makes sense. 0.99, it carries on. The other thing to note, when you're doing this in your SAC or the exam, be careful when you're sketching. Sometimes the examiners will say round to 3 decimal places. And that's a problem because that's rounded to 2 decimal places. Make sure if you're checking your settings, don't just check here. So if you went to documents, if you just clicked on documents and you went down to 7 for settings, the problem with that is that's your calculator settings. It doesn't have graph settings. So that means back to the calculator page, that's what these settings are for. But if you wanted to do with your graphing, okay, because sometimes you have this on 6, that's great. Your problem is your graph. Your graph should be in your menu, this settings. There's a difference between the two. There's the graph settings and there's the calculator settings. This is where you can change.
Most reliable settings.
Instead of float 3, you can go to float 6. See that? Changes the graph, not the calculator. Okay, so that's what happens. A lot of students change it to 6, but then they do this and it doesn't come out the way they want. It's because this is a graph setting. And if you want a calculator setting, it was up here. That's for your calculator. So when you go to menu settings, the 7 setting, that's for your calculator, not your graph. Okay? Anyways, so I've proven that the area is 1, but if you want to find the expected value, you can do this on your calculator. Here's a shortcut, okay, in case you've forgotten or if I haven't taught you. If you do shift, press the shift button plus, that gives you your integration so you don't have to go through the menus, yeah? And the same thing if you wanted to find your derivative, shift minus also gives you that derivative, in case you didn't know. Okay, so now what we want is shift plus, we want to integrate between 0 to 2, I'm pressing tab to move across, and you got x times 0.5 times x dx. And voila, that was 1 1/3, which is what I had before. Okay, so that's how you can do it on your calculator. All right. And in terms of the median, if you want to solve for the median, it's the same thing. If we were doing, I'm trying to find a question with a median. That's fine. Don't worry about that. Anyways, any questions with the calculator so far? Good? All right. Last one for today. Last one for today. Here we go. Here's what I said before. This is the theory that you know for variance. expected value means the mean. This is the error data. Yeah, your data minus my prediction, squaring it, removes the negative, find the mean.
Breaks down
Yeah?
into the stack. I was going to say.
What I want you to see here is this is the formula.
Bring our ranking down.
This is the formula to find out the variance. Well, what's the difference? See, I want you to see what is the difference between this and the expected value. If you find the difference, the only difference is instead of E of x, that was x times the probability, right? And now it's x minus mu squared, then it's x minus mu squared. Yeah, so even if you want to find this, like your computational formula before, I think it was Frankie that gave it to me before. The computational for variance was E of x squared take away E of x all squared, true? Well then if you want to convert this to a continuous probability, it would be the same thing. See, E of x squared would be integration from negative infinity to infinity. Instead of x, you now have x squared times the curve. Minus, okay, so what I'm trying to say to you is that when we say E of x, then it was integration of x times probability. Well then now you've got E of x minus mu squared, then it's x minus mu squared times your probability. Then over here it's the same thing. E of x squared instead of x, I now have x squared times the probability. So you want to do this one now. That minus on that side there would just be integration from negative infinity to infinity, x times f of x dx all squared. See, I've just changed my theory from chapter 13 to chapter 15. That's why I said from the beginning, whatever you learn in chapter 13, you can apply it. It's the same thing. Yeah? And so therefore you can do this question here on your calculator. You can type this in to do this question to find the variance. It's the same thing. Okay, so that's what I wanted to take out of today's session. There was expected value, variance. I revised again what the difference between discrete and continuous was. And you now know, in order for it to be continuous, to work it out, it has to be PDF. It has to be a probability density function. You get that down, that's chapter 15. Okay? Obviously the median was just an extra, but that's the theory. How do we feel about that? Okay, so I summarized chapter 13 as we're going. I'm trying to sort of connect it back to chapter 13, chapter 14, chapter 15. It's all the same concept. One's discrete, one's continuous. Okay? All right. Did I have the solutions for these? Yes, I did. That's the formula that I just showed you why it comes about. And this is what they're doing too. See what I'm trying to say? That's their solutions. They're using the computational formula. E of x squared, if that's x squared, this is x squared. If that is x minus mu squared, that's x minus mu squared. It's the same pattern. And then you've got E of x on the previous question. Square it, subtract them, you get your variance. Cool? I'll leave that there because we only got a few minutes left. But that's exercise 15B. Tomorrow's session, yes, tomorrow's session I will be finishing off this chapter 15 and revising chapter 13, 14, and 15. I want to make sure that those theories stick in your head. Binomial, discrete, expected value, variance, standard deviation, they're all the same. Okay, so if you think about it, there's not much in terms of skill. There's a lot to do for homework, but in skill-wise, there's not much. Expected value, variance, standard deviation, binomial, continuous, which is PDF. That's all you need to know. Technically, there's 5. Only 5 things. Everything else is like conditional, independent events. That's year 11 stuff. Yeah? I'll leave you there, and then we'll continue probability tomorrow. And that way you'll feel invigorated.